So we started doing gravitational waves, the next part of the course, and we spent most of the time last time just introducing Maxwell theory. So this is the second part of the course. And the first topic in here is electromagnetic waves. And the idea here, as I told you last time, was that we know what the electromagnetic waves are, and what we're doing is we're converting what we already know in a language that can be taken over in the case of gravitational waves. Okay. So the first thing that sort of I should say, which we did not discuss last time, is the following, that really the notion of whether a given solution has electromagnetic waves is something that can be really determined only by going asymptotically. So, for example, one might say, well, what about Poynting vector? This is a usual question one asks, that if I look at the Poynting vector and the Poynting flux, because we think of this as carrying momentum, and if the Poynting flux is not equal to 0, isn't it true that there is electromagnetic wave? That is a usual question that one might have. And the answer is no. Poynting vector can be non-zero, and there can be no electromagnetic waves. First remark is that this Poynting vector is, of course, not a Lorentz invariant quantity. It depends on a choice of S frame. So, for example, you could just take just take a Coulomb solution. So I got a point charge just sitting here, right? In the rest frame of the point charge, the magnetic field is 0. So of course E cross B is 0, and there is no Poynting flux. And so we say, yeah, look, okay. With the rest, the charge is just sitting there. Then there is no electromagnetic waves. So this FAB up here will correspond to E, say E upon R squared times the unit time-like vector times the unit space-like vector. I could put hats, but we're using hats for conformal rescalings, so let me not put it. So they're just unit time-like, in this case, space-like vector, and that is the Coulomb solution. So if I put here the with the minus sign, perhaps. So if I put here a time-like vector, then I perhaps have two also. Then if I put a time-like vector, I just get electric field. The electric field is radial. That will go away. The minus sign will go away, and you will just get E upon R squared as the electric field. But if I now go to another S frame, of course, in the new S frame, the Poynting vector is not 0 necessarily, because the Poynting vector is a 3-component spatial component of a 4 vector, and the energy of this Coulomb field, the energy density is not 0. Of course, the Poynting vector will pick up a part of energy density. And if I were to do that, then I would obtain, so for example, I can just do another S frame. So the time translation vector there is going to be given by some sinh of gamma times the original time translation plus cos of gamma times original, say, the vector in z direction. Suppose I perform a boost in the z direction, so the unit z directional vector, unit time translation. So this is a new S frame up here. And in this new S frame again, you can calculate what is E cross B, right? So you can calculate what is E tilde cross B tilde in the new S frame. And this is a very good exercise for you to do. Calculate this, starting from here, where you can calculate E by just dotting this with T. You can calculate B by taking star of this and dotting with T. And then, in the new S frame, the electric field will be given by taking this and dotting with T tilde, and the magnetic field will be obtained by taking star of this and dotting with T tilde, and then expanding it out and see what you get. And then you'll find that you get here something like you get minus E squared upon R to the 4 times beta cos of theta. So there's no beta. is going to be cos gamma cos theta times Rn plus sich gamma times theta. Again, R is a unit radial vector and T is a unit time-like vector. So you get this. So the new Poynting vector is not equal to 0, just because Poynting vector is not Lorentz invariant. And now you can calculate this little flux of this. This is a Poynting vector. Let's call it P tilde for Poynting. So you can take an area element and you can calculate what is P tilde, some area element delta up here times ds. And you'll find that, of course, this is depends on what the area element you choose. This, in general, of course, is a flux of this quantity, and this will not be equal to 0. So if I just calculate the Poynting vector, of a static Coulomb charge, just sitting here, but if I'm moving relative to the charge, then in my rest frame, the flux of Poynting vector is not equal to 0. Therefore, I cannot tell. I mean, if you just say, well, look at flux of Poynting vector, if it is 0 or not 0, that is what is telling me there is electromagnetic wave. Then you have to say that, whether there is a wave or not depends on the choice of a rest frame. In the rest frame of the charge, there is no electromagnetic wave because the Poynting vector is 0. In another rest frame, there is electromagnetic wave because the flux of the Poynting vector in the other rest frame is not equal to 0. That sort of is ridiculous that the notion of electromagnetic waves would not be Lorentz invariant. So what is happening up here? What is happening up here is that this object is falling at 1 upon r to the 4th. But if I went any this area element, and if I took it further away, then this area element up here would go like r squared sine theta d theta d phi. If I take a round area element like that, so there will be r squared here, and so therefore if I take r squared times r squared, I will get 1 upon r squared in the denominator, and therefore the flux out at infinity is actually 0 because of the 1 upon r to the 4th part and the area element out at infinity growing only as r squared. So the statement is that in a finite 2 sphere, the flux of the Poynting vector is not equal to 0. You really have to go at large r. And this is why one says that, well, the radiation field always falls like 1 upon r. If you are a finite distance from the source, I cannot tell which part of the field is radiation and which part of the field is Coulombic, and they're all mixed up here. You really have to go far away, where you can look at 1 upon r part, 1 upon r squared part, 1 upon etc., r cube part, and so on, and then you are able to tell what is the radiative part of the field and what is Coulombic part of the field, and so on. This is just ordinary Maxwell field, but I just want to sort of make you aware of this. But of course, this is exactly what happens also in the case of gravitational fields. Both linearized gravitational fields and exact gravitational fields. And exact general relativity and linearized general relativity. You cannot tell at a finite distance whether there is wave or not. You can look at things like, is there a tidal force? Well, but there is a tidal force even on Earth right now, right? There's a tidal force because the field is not uniform up here. So the tidal force is not enough. So you cannot really talk about gravitational waves or electromagnetic waves. Locally, you really have to go in what people would say wave zone, or in a more precise language, we're calling scry. I think you had a question, Martin?
Yeah, I'm kind of confused what T is doing in a spatial vector like equals B.
Yeah, so this is E tilde. This is in the rest frame of the T tilde vector field. So there will not be R tilde here. Yeah. So T is here just because of the new rest frame. Right? In the new rest frame, T is not.
So those are just the spatial components.
These are just components. These are just, this is a vector, and this vector is some of these two vectors.
Right, so the Tm means we only look at the spatial components of T, or like what are we doing here?
Right, so, yeah, so the statement would be that spatial in the new race frame.
Yeah, yeah.
Right. So, but you don't have to do that. That will all taken care of. The time component of the new race frame would automatically be 0 because there will be a time component here and the time component here. They will both cancel out. Right? So it's not that here you have to do any projection. This vector will automatically be spatial in this new rest frame. It is not spatial in the old rest frame. And the reason is just because E tilde A is just going to be equal to AB, that is equal to B, B tilde A will be equal to star A. So therefore, it is automatically the case, because it is skew-symmetric, that E tilde and B tilde will be orthogonal to T tilde. But T tilde is a linear combination of the two, therefore E tilde is not orthogonal either to Z, or sorry, this should have not R, this should have been Z. Let me just check it. I think it is R. It just comes from here. It just comes from here. Okay, so but it's not perpendicular to E tilde and B tilde are not perpendicular to T or to R or to Z. Okay, so I just thought this is an important lesson. This is this is a typical question that people ask in the first course in general relativity. They say, why do you have to go in the far away zone? I know what locally I can say if the flux of the Poynting vector is 0 or not, and the statement is that the flux of the Poynting vector is non-zero at any finite distance. If you're not in the rest frame of a just point charge sitting out there, the Coulomb field of the point charge would have a non-trivial Poynting vector in a frame which is not the rest frame of the charge. Okay. That's why we have to go to we have to be more careful about what we mean by radiation. So then we looked at Minkowski space. And Minkowski space, we did a conformal completion, and therefore the metric we were interested in Sky plus, and therefore we looked at the metric which was ds squared is equal to, or ds hat squared is equal to omega squared times ds squared, and then d just becomes minus omega squared into u squared plus or minus 2 du r. Omega plus d omega squared. As I emphasized last time, this metric is perfectly well defined. There is no r squared here, so when you go to r equal to infinity or omega equal to 0, this metric is perfectly well defined. So we're taking the conformal factor omega to be equal to 1 upon r, and we're seeing in great detail that this sky that you obtain up here is complete. So the idea up here, as I showed last time, is that there's some source which is given up here. This is our source J or star J, if you look at the tree form, and then it is giving out radiation, electromagnetic radiation, and we go to Sky. Here I'm tailoring everything to Sky plus, but you could also go to Sky minus, and then you just have to use the retarded time V instead of the advanced time U, and you'll get Sky minus up here, you'll get Sky plus up here, and the idea up here is that the radiation is ambiguously defined up here. And we're going to the U and R or U and omega coordinates because radiation is traveling in that direction. And therefore, as you go on U equal to constant, R equal to infinity, you are arriving at Sky. So this is just what we saw last time. And the key point up here was the conformal invariance of Maxwell's equations that we saw last time. And this conformal invariance of Maxwell's equation then implies that if sources is smooth and compact spatial support, right? If it is smooth and has a compact spatial support, then the retarded solution, of course, is smooth. I mean, in the physical space-time also it's smooth, but in the physical space-time Sky is at infinity, and I have to always look at what happens out at infinity. How the things falls off, whereas in the conformally rescaled space-time, Sky is just at a finite distance. Omega is equal to 0 here, omega is equal to 3 here if you like, and therefore this is a finite distance up here. And so the statement, as I told you last time, is that supposing this is electromagnetic wave, if you think of this room as space-time, so this is the time direction, this is space direction, and I got some charge source up here, then I can just go at a finite distance, and I know that the field is smooth. And therefore, what we found was that if I just put f hat AB equal to, I just define it to be equal to FAB, then this satisfies Maxwell's equations in the conformally rescale space-time, and this is smooth. And this is with the sky just at a finite distance, with smooth as sky. Now, this fact has very interesting consequences, and they go by the name of peeling property. So the main point about peeling properties up here is just that the structure, the physical content of this Maxwell field becomes more transparent if you use null tetrads a la Newman-Penrose. The components of this electromagnetic field in the null tetrad fall off in different powers of R, and one of them will therefore represent the radiation field, other will represent the Coulombic part, and so on. This can be neatly disentangled by going to SCRA and by looking at the components in the null tetrad.
So peeling can be proven as a theorem, right? Is it almost formal? And how much? I mean, how does it change if you assume that the asymptotics is not known? Let's say it's a space line.
Changes completely.
Completely. Okay. So the same peeling assumptions that we have doesn't necessarily hold if the asymptotics are different.
Yeah. So if you have cosmology space-time, the cosmology constant, the peeling property. I mean, what I'm just saying here, this method applies. It doesn't care about whether you go to null infinity or not, but the particular rescalings that we're going to get in just a minute, they will depend on where your sky is. Okay. So for this, so the third part of the part B of 1 is just what is called peeling properties. Or actually, first you should say null tetrad. These are the Newman-Penrose null tetrads. We've seen them before, so I'll be a little bit fast. But please, if you have any questions, ask me explicitly. So we're going to introduce these null tetrads up here, and these are in a physical space-time, which are unhatted. This is the physical space-time. This is a confounded rescale space-time. So in the physical space-time, I'm going in excruciatingly boring details, but please pay attention because all the powers of R and such thing all come from here. And this is going to happen also in general relativity and everywhere. So this is very simple, but it is really critical that you have to remember how various null tetrad vectors behave as you go out to null infinity. So the null tetrad here is given by, the n is a real null vector, and our normalization was 1 upon square root of 2 times gradient of t minus gradient of r. And then we got LA, and that was also 1 upon square root of 2 times gradient of t plus gradient of r. And then we have MA, and that is equal to 1 upon square root of 2, r upon square root of 2 times gradient theta plus r sin theta divided by. This factor r up here comes up just because the two-sphere metric is r squared times d theta squared plus, the physical two-sphere metric is r squared times d theta squared plus sin squared theta d phi squared. So physical metrics, two-sphere metric scales as r squared. This is an orthonormal dyad on the two-sphere, so therefore it goes like r up here. So this is the covariant physical metric on the two-sphere behaves like that, and therefore we're going to factor of r in the numerator up here. And you can just check that this is an orthonormal tetrad, that is to say Newman-Penrose tetrad, in the sense that LA and A equal to -1, MA and bar A equal to +1, and all other inner products are 0. So that is the null tetrad that we have. And therefore, just to sort of write explicitly, therefore the contravariant tetrads would look like 1 upon square root of 2 times TA minus RA. This is just the unit vectors. So T dot T is equal to -1, R dot R is equal to +1. These are just unit vectors. LA, of course, is equal to 1 upon square root of 2 times TA plus RA. So this is the outgoing vector, this is the incoming null vector up here, and NA now, because I'm raising the index of the two-sphere metric, and therefore the two-sphere metric with upstairs indices is 1 upon R squared in the denominator, therefore this is going to be 1 upon square root of 2 times R times theta A plus I sine theta phi A, where as usual phi A is just d by d phi, and theta A just d by d theta. So this is very boring, but so this actually is as well R in the denominator, this is R in the numerator. And now we want to go to the rescale, physically rescale space-time, or conformally rescale space-time. Metric G hat AB is equal to omega squared times GAB, and omega is just equal to given by 1 upon R. So we would like to know how these tetrad vectors transform. That is to say, we would like to know what are the corresponding orthonormal tetrads up here. So the main problem is that we want to know if in fact these objects, these tetrads vectors and the co-vectors that I got, whether they have limit as you go out to scribe. So if I just look at the tetrad vector, which is let's look at first of all the vector RA that is here up here. So if I look at the vector RA, that vector RA is just given by GAB times grad AR. So it is GAB with upstairs indices is omega squared times G hat AB grad A. Okay, I have to convert R into omega because omega is a good coordinate at scribe. So this is going to be given by 1 upon omega. So I'll get here minus omega squared. So this will be upon omega squared. G hat AB times grad A omega. And this is what we called when we did null infinity. This is the vector which is normal to scribe because omega equal to 0 on scribe. And this vector is what? So this cancels out. And therefore I get here this to be equal to what we call, I think previously we called NA, but now the Newman-Penrose is called LA. Therefore, just to make a distinction, I call this N tilde I. This is just a definition of N tilde I that I used previously when we did null infinity. Okay. So this has a limit. So the physical vector, unit vector RA, upstairs index, has a non-vanishing limit, smooth limit, and that limit is just given by grad A omega times that. And this is just a null normal to scribe and scribe. Because omega, grad A omega is a null normal, and therefore I'm just raising the index up here. So now I can also look at what is happening to the vector field TA, and TA is just equal to GAB times grad A T. But now T is not one of our coordinates. Our coordinates are going to be U, omega was R, theta phi. So we have to replace T by GAB times grad A of U plus R. Right? U and R are coordinates. And now I just do the same thing now. So GAB is equal to omega squared and G hat AB. U has a well-defined limit at scribe. R is what is happening up here. And you'll find that this actually, in fact, the limit is just equal to this is just equal to N tilde I. So I just leave this a quick check for you. So RA has a limit to scribe, which is at minus N tilde A. That is to say, it is the minus the normal grad A omega with the raised index, and TA has a limit to scribe, which is just equal to N tilde A. It's just 2 lines. Just fill out the calculation, and you will see that. So because of this, you see now what is going to happen up here. If I look at NA is TA minus RA, TA minus RA. So I'm going to get the limit to be equal to N tilde A plus N tilde A. So I'm going to get 2 times N tilde I. So therefore, limit to scribe of NA I'll get 2 times, but there is a 1 upon square root of 2. So 2 times n tilde. And that is the reason why I call it n tilde, because it is not quite normalized. On scry, n tilde and n are both normal to scry, but there is a square root of 2 factor. It's an awkward factor that comes up this square root of 2 all over the place that you have to keep track of, and that's what I got. So limit to scry, I got in fact NA. So NA has a smooth limit to scry. So what have you learned so far? Key points we have learned are that RA, which is just a unit radial vector in a physical space-time, has a nice limit to scry, but is minus n tilde A. The time translation vector field, the killing vector field that we got in Minkowski space-time, it has a nice limit to scry. That's what we see, and that limit is just n tilde A. So let me just elaborate here just a little bit. I should have done it before. So this is TA is a killing vector field, the time translation killing vector field, and we know that every killing vector field must be tangential to scry. The reason is because if I actually move, if I give me the space-time and I attach scry to it, now I perform a diffeomorphism. I perform a diffeomorphism along the killing vector field. It is an isometry. That isometry doesn't change the metric at all. Therefore, it doesn't change scry. Therefore, it must be tangential to scry. It cannot move scry. So every killing vector field is tangential to scry. The physical space-time, this was actually -1, TA equal to -1, right? It's a unit time translation. But in the conformally rescaled space-time, where I got scry, which is a null surface. Therefore, there is no time-like vector, which is tangential to the null surface. Then the vector is either null, which is null normal, or space-like. But this was time-like everywhere. It's a smooth vector field, and therefore it cannot become suddenly space-like, right? So the only thing it can become in the limit is null, because if its norm is positive, it cannot become negative without going to 0, and therefore the statement is that the norm becomes null. And of course, at scry, the null vector field is null normal, so the killing vector field becomes null normal. RA also becomes null normal, but there is no geometrical reason here. Here there is a geometrical reason. In other words, here we really had to do this calculation. Here, just from general considerations, we could conclude that TA must be proportional to n tilde A. But of course, to get the proportionality factor, we actually had to do a little calculation, and that tells us that it is square root of 2 times n tilde A. So is equal to just n tilde A, and therefore NA is square root of 2 times n tilde A. Now what about limit to scry? Limit to scry of LA. Well, for LA, TA is going to n tilde A, and therefore an RA is going to minus n tilde A. Therefore, the limit to n tilde of scry is 0. Limit to scry is equal to 0. So the question is, how does this rescale? But of course, what we want is, so now we got the metric G hat AB, and we got a one null vector, which we can take to be NA. And now I get another null vector. I would like the other Newman-Penrose triad up here. The physical one is going to 0, but I know that n times L is equal to -1. We have that normalization. So similarly, I'm going to get n hat A times L hat A is also equal to -1. That tells me immediately how L should rescale. So I know that GAB, G hat AB, N hat A, L hat B should be equal to -1. But this is the same as omega squared times GAB. N hat A is just equal to NA, doesn't change, or square root of 2 if you want to go. N hat A is just NA. Okay. And then L hat A, I want this to be equal to -1. But I know that GAB, and A, LA, LB is equal to -1. So that immediately tells me that the null vector L hat B up here should be equal to omega to the -2. So the statement up here is that L hat A be equal to omega to the minus 2 times LA, so that G hat AB, M hat A, M hat B is equal to minus 2. Okay. So it's a null vector. So this vector goes to 0 very rapidly. This goes to 0 as omega squared, so that is to say as 1 upon r squared. That's what we see up here. You can also do the calculation explicitly and check that it goes to 0 as 1 upon r squared. And what about m and m hat? So by the same logic, namely m, you just replace this m by 1 upon omega, or this ma to be by omega up here. That's by the same logic. You would find that m hat a should be equal to, so m hat a should be equal to this, so therefore it should be equal to omega minus 1 times ma, and similarly for the other thing. So these are the facts, these are the things that we get. So in the physical space-time, you can write down as n hat a is equal to LA, n hat a is equal to r squared times LA, and m hat a is equal to r. So in other words, ma is just this vector field, 1 upon square root of 2 times theta a plus I sine theta d phi. It is just the ma vector field on a unit to sphere that has just gone away by a conformity scale. Okay. Is this clear? Are there any questions about this? This is very straightforward, very simple. Geometrically, what is happening is that out of this null tetrad, Na does not change. La is going to 0 very rapidly, so we have to rescale it by 1 upon omega squared, or multiplied by r squared. This is going to 0. Similarly, Ma upstairs is going to 0, so we just rescale it, and we obtain some vector which has a limit to sky. So this is our limit. Okay, it's very simple, but just remember this. And this is something that happens in this form. It is something that happens also in any general curved space-time. It doesn't have to be Minkowski space. We have looked at the Minkowski space for explicit calculations, but this, everything I've said is true in the general curved space-time. I mean, in the general curved space-time, I would not have canonical coordinates theta, phi, etc. But if you're given a physical Newman-Penrose tetrad, then the Newman-Penrose tetrad, which is well behaved in the conformally rescale space-time, will be related to the one in the physical space-time just by these factors. Okay, everything is okay. And this is what also going to be true in full nonlinear general relativity. That's why I did this in excruciating, boring detail, because please remember all these factors, and they're non-trivial. It's not something that we're going to just guess immediately. It's something that you have to work out. That this doesn't rescale, this is rescaled by 1 power of omega, this is rescaled by 2 powers. Now this immediately tells us very interesting properties which go under the name of Peeling theorem. So the way that just as in the literature the Peeling theorems are done slightly differently, I find this is a much clearer way of doing Peeling theorem, not because of underlying mathematics, but just underlying physics. Because now the Peeling theorems are just going to come out of the fact that the field F hat AB is smooth as Scri. You don't need anything else. Why is it smooth as Scri? Because of conformally invariance of Maxwell's equations, the field is completely smooth as Scri. In the case of gravitational field, we don't have conformally invariance for Einstein's equation. Therefore, smoothness is something that will be just assumed for the solution. That is to say, if we'll call a space-time asymptotically Minkowskian, if in fact Scri has sufficient the metric at Scri has sufficient differentiability. And again, this idea of peeling will follow word by word in that case. Okay. So now, so part 3 is the Peeling theorem. And the point about this Peeling theorem is just that it enables us to extract physics out of this full FAB or F hat AB. A full FAB, F hat AB is a 6-component object. It satisfies various equations, and as we'll see now, the structure of what happens at infinity becomes clearer, and we can extract the part of FAB which has radiation field. And thus, for example, and this extraction is going to be invariant under Lorentz transformation, and therefore the radiation field, either there is radiation field or there is no radiation field. So for the simple example of the Coulomb field that I just wrote down up here, we'll find that the radiation field is 0. Doesn't matter what frame you evaluate it in, it's just 0. Okay, so what are the peeling theorems cover? The first thing is that there's always a pedagogical way of doing it, which is slightly easier, so let me follow what it does. Right. So first we start with a conformally rescaled space-time. So in M hat G hat AB, what we have is a smooth field F hat AB and smooth tetrad vectors N hat A, N hat A, and N hat bar A, which are smooth vectors. These are the Newman-Penrose. So everything is smooth up here. And this is the notation. You define phi 2 to be a component of the Maxwell field in such a null tetrad, FAB times NA times NB. And we define phi 1 to be equal to 1/2 FAB times NA sorry, N bar B, not NB, NLB plus NA bar B. And then we define phi 0 to be equal to FAB. For some reason we change, becomes this NA. These are just definitions, no particular significance. As I mentioned to you a few lectures ago, this becomes much more natural and completely natural notation if you use spinors. In spinor language, these are just the obvious components that you would consider. In the tensorial language, they look a little bit awkward, but that's what we do. So these are, because of M bar, because of M, and because of M bar up here, these are complex. So this is the real part of phi 1 naught, phi 1, namely FAB MA and bar B, and FAB MA and bar B. This is Q symmetrized, and this is the imaginary part of phi 1. So the statement up here is that these are 3 complex quantities. Not very profound. They have the same information as in the Maxwell field. If you give me a Maxwell field and a tetrad, I can construct this and conversely. So it's just a component. Now just a side remark, because I've seen students getting confused about this. Very often they are called Newman-Penrose scalars. Phi 0, phi 1, phi 2, they are called Newman-Penrose scalars. And then as soon as you hear the word scalars, you feel that that means they're invariant. Well, they're not invariant, they're clearly components, right? So if it depends on the choice of your chart. If you change the chart, they're going to change up here. But they're called scalars in the sense that they are coordinate independent. If you give me these vectors, then these quantities are just scalar products, just contractions of the Maxwell field with various vectors. Therefore, if I make coordinate transformation here and coordinate transformation here, they don't change. It's not a very profound remark, but scalar does not mean it has any invariant quantity. Some people, sometimes you will call them Newman-Penrose invariants. They're not invariant at all. They depend on the choice of tetrad, null tetrad. We just happen to choose one, but you can choose another null tetrad at Scri. At Scri, the only canonical vector that I got is a null normal to Scri, which is n, and even that can be rescaled. And L and M and M bar is our choice. We just made one choice by using some Cartesian coordinate systems. In particular, we use a particular vector field T and R and so on and so forth, and that gives us choice. It's a nice choice, but it's a choice. There's no God-given reason from the point of view of Scri to just stick to that choice. So these are just 3 complex quantities. And now, the point is that at Scri, so these are functions of U, omega, theta, phi. At Scri, omega is equal to 0. Therefore, at Scri, the evaluation of phi 2. When I say Scri, this case, I'm just always been scribe plus. It could have been scribe minus. I can do the same thing with scribe minus, but then I have to use the coordinate v. For concreteness, I'm just using the coordinate Europe here. So at scribe, this is just Euro this is just written as evaluate at scribe is called as phi 2 naught, and this is a function only of u theta phi. So it's a function on scry. Scry is u going this way and theta and phi going this way. That is 2 cross r topology up here. Scry is doing that. And then this phi 2 naught is just a function here. It is the leading order behavior of phi 2. And if you like, what I can do is I can do a Taylor expansion of phi 2 in the powers of omega. Omega is equal to 0 here. So I can write this phi 2 as phi 2 naught plus omega times phi 1 naught, which will also depend on u theta phi, plus omega squared times some other thing, some other coefficient time, which will also depend on u theta phi, etc., etc. So I can do this partial expansion if I want it. And this is just the leading order term. So you see again and again in the literature, in numerical relativity and so on, what people will be plotting is quantities like this. And this naught just means the leading order component of this conformally invariant, of this component in the conformally rescaled space-time of the Maxwell field. And similarly then, I got phi 1 naught, which is a function of u theta phi, and I got phi naught naught u theta phi. So the downstage index up here, the covariant index, tells me which component I'm looking at. This component, or this component, or this component. And up here, 0, that just says that this is the leading order component, a leading order part of this particular component, leading order part of that particular component, leading order part of this component. So these are the parts we just have evaluated and scribe, and that's what we have here. Okay, and now the next statement is extremely simple. It is just that we know by definition that all these fields, phi 2, phi 1, phi naught, these are all smooth in the physical space-time. We've got smooth FAB and we smooth these things, and therefore these Newman-Penrose components are all smooth in the conformally rescaled space-time. But now what I would like to do is, I would like to relate them to what is happening in the physical space-time. And that is very simple. So if I was interested in the physical space-time components up here, then I would write down here phi 2, physical space-time, I would write down phi 2 up here, and phi 2 will be exactly that. So this should have been. So I made a mistake. I apologize up here. Here I should call it phi hat, f hat, phi hat, f hat. Okay. So these are all I said here. They're smooth f hat AB, and these are the tetras. But when I wrote down, I just wrote down the tetra things without hats. That was a mistake. I should write down everything in terms of hats. And these are the smooth quantities as graph. What about phi 2 in the physical space-time? I would just write this as FAB times times NA and B. So it is not phi 2 hat, but it's just equal to phi 2.
And bar B, right?
Yeah, and bar B. Thank you. And bar B. Thank you. But this is, I know what this is. Conformal invariance tells me that this is equal to f hat AB is equal to FAB. So this is f hat AB. NA is the same as n hat A. But M bar, on the other hand, M bar is equal to, I can write here. So M bar is equal to 1 upon R times M hat. Therefore, this is just given by phi 2 divided by R. phi 2 is given by phi 2 hat divided by r. This is just phi 2 hat, this is phi 2 hat divided by r up here. So therefore, if I were to look at this phi 2 as a power series constant 1 upon r, it would look like phi 2 naught. Phi 2 naught is just the leading order behavior of phi 2 hat. So it will look like phi 2 naught u theta phi upon r plus higher order terms. If I were to Taylor expand, I will get plus order 1 upon r squared. What about phi 1? Well, phi 1 is 1/2 FAB times NALB plus NAM bar B. And again, this is given by 1/2 of FAB is a hat AB. And A is in hat A. But L is different. We see here explicitly that L is equal to 1 upon r squared times L hat A. So I get here and what about M and M bar? Well, M and M bar are both each of these terms will acquire 1 upon r from here. So therefore again I get A. Therefore this object is just equal to phi 1 hat, denominator is phi 1 hat divided by r squared. And therefore we find that this object is just given by, again if I were to do the leading order term, I will get phi 1 naught u theta phi, which is, I'm just expressing this, the leading order behavior of this, upon r squared plus terms of the order 1 upon r cubed plus higher order term. So we see something quite nice, namely that the physical quantity phi 2 naught, right? It's really, it has a, phi 2 naught is a coefficient of 1 upon r part of the Maxwell field, and phi 1 naught is a coefficient of 1 upon r squared part of the Maxwell field. So we got nice separation about parts of the Maxwell field which fall like 1 upon r squared, and to nobody's surprise, phi naught will be 1 upon r cubed part of the Maxwell field, as we will see just now. And that's why it's called peeling. It is as though the Maxwell field is peeling off. This is 1 upon r. I mean, as you go out to infinity, phi naught will first peel off. It will fall off like 1 upon r cubed. Then this will peel off. It will fall off like phi 1 will fall off like 1 upon r squared, and phi 2 will fall off like 1 upon r. Okay, let's just finish this and then I'll ask questions. I'll take questions. If I look at phi naught up here, so this is just equal to FAB times MALB. And now the statement is, this is the same as F hat AB. Right now you are experts. FAB is F hat AB, and this end. This is why I did this in expression in more in detail up here, because this is what is really giving us a speeding behavior. Namely, I get here FAB times MA, and MA is given by 1 upon R times M hat A, and L is 1 upon R squared times this thing, and therefore this is given by phi naught divided by R cubed, and therefore if I were to do an expansion, this would look like phi naught naught u theta phi upon R cubed plus R upon R to the 4. Of course, there are parts 1 upon R to the 4 here also, there are part 1 upon R to the 4 here also, etc. But the statement up here is that if I take the R times phi 2, then I will get the leading order behavior here. If I take R squared times phi 1, I will get the leading order behavior of phi 1 naught here. If I take R cubed times phi naught, then I'll get this leading order behavior. So we get this nice way in which the Maxwell field is speeding off. Phi naught is falling like 1 upon R cubed as you go to scry. Phi 1 is falling like 1 upon R squared, and phi 2 is falling like 1 upon R. And this is what we're going to use in a minute. Yeah.
So none of the phi hats actually vanish at the square by assumption?
I mean, they could vanish as scry.
But in general, the leading orders are all order omega 0, right?
Yeah, it's a value at omega equal to 0. Is the value of phi 2 hat at omega equal to 0 is phi 2 naught u theta phi. The value of phi 1 hat at omega equal to 0 is u theta phi 1 0 times u theta phi. So the value of phi 2 hat is 0. So for example, if you have Coulomb field of a charge, phi 2, then this is 0. This term up here will be 0, and that can be 0.
Okay, but I guess what I was saying was that you don't assume that when you Taylor expand phi hat in omega, you don't assume that the first term is proportional to omega. You assume that the first term could be constant, and then the next term is order omega, then the next
Right.
Okay.
It's a smooth field. So supposing I'm doing, right, let's do it slowly. So this is omega, so omega I can just write as a axis up here, omega is omega to 0. And I have all these phi 2 hat, phi 1 hat, phi 0 hat. They're all smooth functions, right? And I'm doing Taylor expansion.
Yeah,
so the value of the Taylor expansion is always going to be the value here plus omega times something and plus etc. So it's not,
I was just wondering if peeling was saying something stronger about some other phis, like that would necessarily have to vanish as well.
no. So the statement here is that just
Okay.
all these quantities in general are non-zero. Of course, in some particular example, I mean, if I'm doing Taylor expansion, in a particular example, something could be 0, but in general, it could not be 0. Okay. So why is this of interest? And this is what we now are going to see. So this already suggests to us, or I should not perhaps erase this. This already suggests to us that in fact, phi 2 naught, or phi 2 in general, should be thought of as a radiation field because it falls off in the physical space-time. Phi 2 falls off like and similarly I got for phi 1 and phi 0. So you can think of this as being falling off like 1 upon r, and therefore you might think that this is really the radiation field that we should think about. And as we will see in a minute, this is indeed the case. So the next topic to see that this is a radiation field really, I mean, it's falling at 1 upon r, so you already may want to call it radiation field, but there's a stronger reason, and that's what we're going to see right just now. And so the next topic, D up here, is going to be a detour into what is called spin-weighted function. So spin-weighted functions or spin-weighted calculus of spin-weighted fields. So that's what we want to do now. So this has to do, so I'm jumping because we just need this material. It's all very elementary, but you have to understand it once. So the point up here is as the following, that when you look at spin weights, we forget about R and theta, sorry, R and U behavior, and we only concentrate on theta phi. So we look at the two spheres. So spin-weighted objects have to do with quantities on two spheres. So they have to do with fields of two spheres. I would want to say that you can do everything without ever thinking about spin-weighted objects, but it's just that it's full of, in the literature, it is used very, very often. And it's also true that when you want to do calculations, they often become simple in using spin-weighted. They bring out some structure that otherwise we would have to struggle a little bit more to extract. So this just is fields of a two sphere. That's what the spin-weighted objects are. So on the two sphere, we've got this M hat A, M hat bar A. On the unit two sphere, so we got this M hat and M hat bar, and these are, as we saw, the metric is really that of a unit two sphere on scry, and these are the vectors that we got here, and therefore we really have M G G A B, G hat A B, and hat A B. These are complex vectors, and they satisfy this condition. But this basis, even if you give me a two sphere, you get a metric on the two sphere, but you don't have orthonormal vectors M A and M hat, M hat A and M bar hat A on the two sphere. Right? So there's a freedom here, and there's a gauge freedom. And the gauge freedom, these are complex vectors. So the gauge freedom is that M hat A goes to some e to the I alpha. Depends on theta phi times M hat A. This is the freedom that we got. under this orthonormality condition is satisfied. So basically, we got a freedom of rotating this complex null tetra by a U1 transformation that we have written down up here. So this is a gauge freedom we have, under which, under this transformation, if I look at the two-sphere metric, SAB, which is given by MA, M bar B symmetrized, this is invariant. And the volume form, two-dimensional volume form, which is given by 1 upon R. That is also invariant. So this is the metric is invariant. The volume form to orientation is determined by the metric, and therefore this is a continuous transformation, and therefore sign cannot change, and therefore we're looking at the metric being invariant implies that the volume form would also, or area form would also be invariant under this thing. So therefore the statement is that if you've got a field, a function, oh maybe I should. Now suppose you consider a vector field of one form, VA, and I can expand it out in the basis, and I'll call it F bar times MA plus F bar plus F times M bar. I'm assuming this is real for simplicity because we're going to be interested in real. And so this is just a component along MA, and the complex conjugate will be a component along M bar A. Okay. I just do it. So the point is that if in fact MA changes under this gauge transformation, V of course has never heard of MA and M bar A. V is just a physical vector that you're given, like for example the electric vector, electric field or magnetic field or something. Of course that doesn't change at all. But on the other hand, MA and M bar A changes, therefore F and F bar change. So F is going to change by e to the I alpha times F, because M bar changes by e to the minus I alpha times F times M bar, therefore F changes by e to the I alpha, and F bar therefore changes by e to the minus I alpha times F up here. So this quantities which scale under change by e to the I alpha are called spin rate 1. So we say F has spin rate 1. So anything which changes by e to the I alpha will be spin rate 1. If in fact I got some quantity, some other quantity G H, which changes by e to the 2I alpha or Si alpha in general. S is an integer times H. Then this is H is supposed to have spin rate S. And of course, this H would in general come from just a tensor field, PA1 up to AN. And if I were to expand this out, in particular, I will get a term which is M bar A, M bar B, sorry, M bar A1, M bar A2, up to M bar AN, AS. This quantity will be H, this quantity H up here. And this H has, because T does not change, this H has a spin rate, is going to have spin rate S in general. So here we have got spin rate 1, the coefficient M. There I got some, I did it wrong here. So here I was expanding the vector, here I'm contracting the tensor. Therefore, if I have S contractions with M, then I got spin rate S up here. So basically, M has spin rate 1 and bar has spin rate -1. Right, we're to finish in 1 minute. we still have 5 minutes. Okay. So M has spin rate 1, M bar has spin rate -1, and that's the and then the statement is that if I contract something, this has no spin weight because it just doesn't care about M at all. If I have M contraction up here, then that is going to have a spin weight as in. Okay. So these are the spin weighted quantities up here that we get. And now, so if you like, spin weighted functions are just a simple way of talking about components of tensors in a two sphere, right? They're components in the basis M bar. It's not very profound. That's what it is. So I could just live with just tensor fields on a two sphere and never have to worry about the spin weighted functions. Never have to worry about components in M bar. But again, literature is full of the spin weighted quantities, so you should know about them. And so, for example, as we saw, we have got these various quantities that were written up here. Phi 2 hat, this quantity up here has spin weight -1 because of M bar up here. This is M and M bar, 1 and -1 they cancel. No M and M bar, no. So therefore consistent. This is spin weight 0. And this object up here has spin weight 1. Phi 1 not because of this has spin weight 1 up here. So, and now the only thing that you would have to know is some strange looking derivative operator, and that is called F. So there is an angular derivative operator. Which I call F up here. And this angular derivative operator is defined as follows. This operates on these spin weight quantities. So F operates on spin weighted quantities, spin weight M, spin weight S up here. And this is just given by 1 upon square root of 2 times MA times, this is just the two sphere. I put an under bar here to denote that this is a two sphere covariant derivative. Times Fs minus S bar square root of 2 times cot of theta times Fs. And the coordinates, so this is the last thing we'll do, and then we're almost done up here. And the coordinates, it just becomes 1 upon 2 times d theta of Fs plus I upon sine theta d phi of Fs. So Fs is a spin weight S function minus S cot of theta times Fs. So it's a messy looking definition, but its origin is very simple. And we'll just do that and then we'll stop. So supposing you are given this vector VA, and I take its derivative VB. So we are given this one form VA, that is given to you, and I take its derivative VB. And then it's natural to evaluate, for example, MA and B, or MA and bar B, or M bar A and bar B, etc. I just give one example. Now this, everybody knows, can be just written as MD BB of VAMA. Just using Leibniz rule, I'm taking this inside and minus MB DB of MA times MB times V. Right? I just took M inside and I'm just correcting it for it. I'm just using Leibniz rule, not very profound up here. So this is given by that. Yeah, I'll just finish in 1 minute, or a minute. So what are we going to? So this is the formula that we got. But this quantity is exactly MA, VA, MA is precisely this F. This F. Spin vector 1 quantity. So this is equal to MV dB of F. And instead of writing F, I will let me write as F1 now, because to reflect the fact that it's spin vector 1 minus, I'm going to get here MV dB of MA right, times VA. And I can expand out this also in terms of M and N bar, but let me not do that. So we just get this, and now you can see that this quantity up here is the same as this quantity up here. And this quantity is just a connecting factor. So this derivative looks very mysterious. Where did all these things come from? And they just come from the fact that this is a covariant derivative. Spin-weighted quantities refer to the contractions of tensors with m's. And now, if I were to take it inside and get a spin-weighted quantity, then I have to correct by this derivative operator. I can expand out this VA, and as I did up here, I can write as F bar MA. That's F M bar A. And I can simplify this further and just a little bit further, and I find that I get exactly this if I actually use for my M and M bar the formulae we had written down before in terms of the d by d theta vector and d by d phi vectors up here. So this is called our object H, which operates on spin-weighted quantities and always increases the spin weight by 1, because I get one more F up here. This was spin weight S, I got one more F, therefore I got additional spin weight coming up here, and again I got here. So it increases the spin weight by 1, and this is what happens. And that is just expanding out in terms of this basis. So these are the explicit formulae, and we're going to use that. What we'll see next time, when we begin, is the following. That we got these fields up here. We got these leading order fields phi 2 naught, phi 1 naught, phi naught naught. This is the coefficient of 1 upon r, and therefore we suspected that this is like the radiation field. And now what we will do is to write down the Maxwell's equations on scribe. And to write the Maxwell's equations, we will use the derivative along d by du, and we will angular derivative, which is going to be f. So Maxwell's equations can be written as d by du derivative and f derivative. And what we will find is that there is no condition on phi 2. Phi 2 is unconstrained. Maxwell's equation says nothing about phi 2. On the other hand, Maxwell's equation says that the time derivative of phi 2 is given by f, or the angular derivative of phi 2. So time derivative of phi 1 is given by angular derivative of phi 2. So there is no dynamical freedom in phi 1. If you give me what phi 1 is at u equal to minus infinity, I know it everywhere. The time derivative of phi 1, phi naught, will be given by angular derivative of phi 1. So if you give me the value of phi naught in the distant past at u equal to minus infinity, then phi 1 will determine it everywhere. So only a freely specifiable object is this phi 2. And that phi 2 determines all these other things completely except for initial values. And therefore, the freedom in giving the solution to Maxwell's equation is really, there is a three-dimensional freedom, and that is in phi 2. And then there is a two-dimensional freedom here, phi 1 and phi naught. These are just initial values. And that is why this is called the radiation field, because it can be arbitrary. You can wiggle your source and do something, and that field is arbitrary. But phi naught is not arbitrary, and phi 1 is not arbitrary. Once you know what phi 1 is at one instant of time, you know what it is for all the instant of time up here. So this is why this field is called the radiation field. And then you would expect, oh, good. Now I got the idea that in fact I got the radiation field, and therefore how much is energy carried by electromagnetic wave, how much is momentum carried by electromagnetic waves, that all should be expressed completely in terms of phi 2 naught. We'll see tomorrow, next time, that is the case. So this is the reason why we are giving so much importance to this radiation field. And then in the case of gravity, both linearized theory and full nonlinear relativity, there are analogs of this phi 2 which capture the radiation field in the gravitational field, in the gravitational waves, and that is what numerical relativists want.